I did see JJ. Yeah, JJ is with us. I think that's the most important one. The rest of the guys, yeah, can just pop in as the session go on. So yes, welcome everybody. Today will be the third and the final session on DFC software for this year as part of Simtech's Lunch and Learn series. All of the previous sessions we had on the 23rd of May and 18 July was recorded, and you can find it on our YouTube page, together with all the other sessions we had on these topics, as well as other topics we cover on MSC 1 that you can find on our YouTube page as well. To see what sessions are next, you're more than welcome to visit our website and navigate to the training section. If I remember correctly, I think what's left for this year will be on CAE fatigue, on 𝗬𝗏𝗍, and the nonlinear FEA solution MARC. For those of you that doesn't know, 𝗬𝗏𝗍 is the AI and machine learning solution that we have within the MSC 1 licensing environment. So as I say, today will be the third session. In the previous topics, just to recap a little bit, we covered a broad range of topics. The first session, I discussed the high-level overview of the product of DFC software, covering how it complements the world-class solutions of MSC Apex, MSC Nastran, and Patran, the typical workflows that's involved in stress analysis, as well as how DFC software ultimately automate and standardize these workflows and the job for the stress engineer. The second session went a bit deeper into the details and application of DFC's software. We used the typical examples of fasteners and stiffened panels to demonstrate and explain the workflows in DFC, both of which are very much used in aerospace structures. Today we will cover two additional examples that we find both in the aerospace and space applications. However, it is not limited only to these industries. One can utilize DFC software for any design application where multiple load cases and certifications are required, and obviously if you want to automate those processes. Okay, so I'm not going to go through all of the details of the ins and outs of DFC software and the nuts and bolts behind it. These are covered in the previous sessions. I can maybe just recap or summarize that DFC software is a powerful solution to ultimately bridge the gap between designs and certifications in an automated and standardized way. Maybe just looking into the analysis methods and calculations to evaluate the structural design. We've covered this in the previous sessions as well, but just briefly, DFC software bridges the gap between the approved methods and that's recognized by certification authorities and the results generated by FEA models. So in order for us to get to a RF value or a reserve factor, we need to compare an allowable load with an applied load. Now, dependent on the industry or the region or the continent that you live on, this can also be defined as, or is also known as a safety factor. The allowable load is defined by methods and data sets recognized or approved by certain certification authorities for that industry, or even by companies themselves, while the applied load is generated by the structural simulation tools like MSC Nastran and other predefined guidelines and recommendations. So moving on to the topic of today, we will discuss the topics of composite analysis as well as dynamic analysis, which is comprised by frequency response analysis and random analysis. Maybe just briefly, before we jump into the details of it, and before I hand over to JJ Joubert, that will cover these topics. Just need to mention that DFC is populated with numerous methods and predefined analysis techniques. However, it is not limited to those as well. Companies, users, OEMs or more is allowed or is enabled to use their own analysis data, their own techniques, their own formulas, their own methods or IP that they can plug into the software and ultimately automate the process between an engineering design, the analysis associated with that, and the stress report that can be used for certification purposes. So yes, for today, like I say, JJ will cover the topics of composite analysis and dynamic analysis. JJ, if you are there, you're more than welcome to share your screen. While we wait for you, just again, we will cover these two topics. We've covered fault thinners and stiffened panels in the previous sessions, but there are several other methods and calculation sets that's included in DFC that we can cover upon request or for specific applications that you guys are welcome to contact us. Cool. JJ, welcome. Thanks and hello. Appreciate you helping us out again.
Thank you, Zak. Hi, everybody. Just want to get rid of this. Okay, there we go. Right. Thank you, everybody. Thank you, Zak. So today we're going to be covering two topics available on DFC, and that is first one is composite analysis. The second one is the dynamic analysis capabilities of DFC. So let's kick off with the composite analysis capabilities. So firstly, what is a composite? So composite is a stack of layers made of orthotropic material. That layer typically consists of a matrix or a resin that bounds the fibers inside that laminate together. So that is typically a composite, and those layers are stacked at various angles relative to each other. So that's typically a composite. So just briefly, the value added by DFC in these analyses are that we have several fiber matrix failure criteria, fiber separate, matrix separate, and then there's also criteria that does not distinguish between whether it's a fiber or matrix failure. So we've got a lot more that's available in standard in Nastran. And the big other advantage that we have is that we can we have a method for progressive failure analysis that we add with the methods, and that method is it's a complex and time-consuming process. So again, DFC manages this analysis process in a simplified, standardized, and automated way with proven methodologies to minimize calculation errors, save costs, and save time. Right, so the topics we're going to cover today is just the explanation of the failure criteria, how you can assign stacks via DFC to Apex, how we perform a laminate plane strength failure analysis, the laminate shear failure analysis, then a progressive failure analysis, and our open hole analysis. So again, we look at the formulation of an RFs. So RF is the allowable criteria over applied criteria. So the allowable data for composites, so those are always obtained by testing on laminar or ply level or laminate or layup level, depending on what you're analyzing. So on the applied load side, we extract loads, elemental loads from the Nastran results for the analysis. Why loads? We want to use loads for the progressive failure analysis. We want to use loads for failure criteria that's not available in Apex or Nastran.
And for 𝗀𝗁𝗍𝗏, which is the dynamic analysis part of Nastran, they do not support any ply stress output for any calculations. So that's why we use loads. And then once we have the loads, then we calculate the ply stresses and strains using classical laminate theory. All right, so let's look at failure criteria. So we have several failure criteria available in DFC. So there are basically three groups. One which just looks at the failure of the fiber. The other group just looks at the failure of the matrix. And the third group is there's no differentiation between failure modes. So this is basically how we've divided these the criteria that you can use just for fiber, just for matrix, no differentiation. And then for UD, you can use any one of these to do a UD failure analysis. And if you've got woven fabric, then you are limited to those failure criteria listed there. So again, we have several of these available in DFC. Just a note on failure criteria, how it's actually been developed. So basically what they do is they have a little test coupon, and they do tensile and compressive tests of the material at various offset angles with respect to the one axis of the ply. And then you get a curve, something like this, that gives you the allowable stress versus an angle. And then all that they do is with the failure criteria developments, they do curve fitting to predict the failure at applied stress at an angle. So this is what you get from the test, and then they typically do something like this to do a curve fit based with input parameters of your allowables and dimensions and things like that, the parameters, and they do a curve fit of it. So these are typical Yamada-san, Hill, Hoffman, and Cy-Wu max stress curves, and you can see that all of them are more or less the same. So that is typically how a failure criteria is developed. So the next example here is to do stack assignment with DFC. So what we do there is most composite designers use Excel to design the stacks by defining the material thickness and ply angles in an Excel spreadsheet. So we also have an Excel spreadsheet that you can design stacks with, and we then use this Excel spreadsheet data to allocate the ply stacks directly to Apex, and we automatically create the sheets, the stacks, and assign that to the panel faces that you selected. Here's just then a quick video to illustrate the process. So yeah, switch off. Bye. Get this thing started. I'm not
you just need to switch off her laser, JJ.
Yeah, I'm trying to do that.
Well, okay, no, I know usually when you use the laser, it doesn't want to point to the control of the of the video.
But now my laser is stuck somewhere. Switch it off. Switch it off. Come on, I want to switch it off. Sorry about this. Okay, let me just do that. There we go. All right, so in the spreadsheet, you add your materials, your material type, woven or UD, and thicknesses, and then you can design your stacks inside the spreadsheet. So it just a drop-down menus automatically selecting the material, and you specify the angles, and then you have a little nice tool to define where the stack data is located. Coming back to DFC, then we import all those stacks that's been defined in the spreadsheet. So there we import all the data for all the stacks that you've designed. Then we go to next step is we go to Apex. So in this case, we already have a stack assigned. So this is to show that we can modify or add stacks to current data.
So basically, you put on your geometry pick filter, you select your face where you want to assign the stack to. Go back to DFC, select your stack, and you assign your stack via DFC. So now Apex is updated with all the required data. So if we go back to the panel, we will now see that the new stack has been assigned to that panel. So there's the plies with the new thicknesses and angles. And as mentioned, if we go to our little table for sheets and stacks, we automatically create a sheet in DFC in Apex, and we automatically also create the stack inside Apex. So we go through the whole process. So all you need to do is select the stack, select the face, and press a button, and you'll take care of the rest. Right, so that is stack assignment. So that's the next one is laminate plane strength failure analysis. So as mentioned, we extract elemental loads from the Nastran H5 file. Then we calculate laminate strains and stresses using classical laminate theory, and we then calculate the RFs as per your selected failure criteria. So the standard output for in Nastran is, it will give you a failure index. And just note that the RF is not just 1 over the failure index. Depending on the failure criteria that you use, for example, Hill, your actual RF is calculated like this. So the way to calculate an RF depends on the failure criteria that you use for your analysis. Right, so if you look at, so that is plane strength. So if you look at interlaminar shear strength, again, here we extract elemental loads. Then we calculate the interlaminar shear stresses with the theoretical method using static moments, calculate the shear stresses, and then we calculate the RFs. So for normal bond ply indexes, we calculate the RF like this. And for honeycomb core, we use a slightly different way of how to calculate the RF for honeycomb core using the stress ratios for your core allowables in the XZ and YZ directions. So that's interlaminar shear failure. So let's come to progressive failure. So this method is based on a method given mechanics of composites of Jones. So basically, what they do is you have your laminate, you calculate your ABD matrix, and you have an applied load. Then you calculate your stresses in your laminar, and you apply your failure criterion. If that laminar, then all the laminars that fail, then you basically degrade the stiffness matrix. In other words, you make the stiffness of that laminar, you make it basically 0 by setting your Young's moduli in E1 or E2 and G1 to 0. So then you calculate the new ABD stiffness matrix, and you repeat this process by progressively increasing the load and degrading your stiffness matrix until there is no laminar left, and this will then give you gross laminate failure. So we use this principle, but instead of incrementing the load until we get failure, we use the RF. So we have a constant load, and we use the RF calculate and the RF data calculated to degrade the stiffness matrix. Right. So our normal Nastran input gives us first failure. So basically, it tells you something has failed. You don't know whether it's fiber or matrix, but something has failed. Then what we do is we were actually interested in when the first fiber is failing. Now, it's not the matrix, but when the fiber is failing, the first fiber fails. So that is more or less at this point here. If you look at so this is typically a graph of load versus displacement of a test sample. You get first failure, then you get first fiber failure, and eventually you get laminate failure, which we call then last fiber failure. So how we do it again is we have our applied loads, we calculate our stiffness matrix, then we calculate the laminar stresses, we apply our failure criteria. If the matrix is got the min RF, we degrade the matrix stiffness, the stiffness properties, update the ABD stiffness matrix, and we repeat this process until the min RF is for fiber. And that gives us our first fiber failure. And then the RF then obtained there gives us the min RF for first fiber failure. If we now move on to last fiber failure, so what to do here is just keep on repeating that process as for the first fiber, and we keep on degrading the stiffness matrix. And in this process, every time we degrade it, we record the RF of that process, and the iteration is stopped when we have a singular stiffness matrix or there is no lamina left for the calculation. Then we have a look at the RFs that we've recorded for the previous steps, and the maximum of those RFs then gives us the last fiber failure RF for laminate. So in other words, that's when gross laminate failure will occur. So just to put this in an example, so when a single ply fails, it does not mean that you have a complete laminate failure. It's just the ply that fails. We still have plies that are intact. So what happens is that the load is then redistributed to the other plies, and they will progressively fail until you get gross laminate failure. So in this example, we have a little test coupon with a tension load applied to it. We have a 0.45-45-0 layup. So if you do now a first failure, then you typically get an RF of 0.53 in this example. So that is when something fails, the first thing that fails. And this example, it's one of the matrices that failed, probably of the 45 stuff that failed. Then we do the first fiber failure. So the first fiber failure is when one of the first fiber fails, and then you get the RF of 1.036. And you keep on until you get last fiber failure. You then get apply RF of 1.849. So why is this possible? If you look at the load direction, remember fibers only carry load more or less in the direction of the fiber. So if you've got a 45-degree fiber, they're not really very efficient in carrying the load. So the matrix and things will fail, and eventually you only end up with a zero ply. In this case, the zero ply, which is in the direction of the load, one ply is enough to carry all the load. So you actually don't need all those other plies for this specific case. So this is the principle of progressive failure. And the other one add-on onto this is you can use this to optimize your ply layup. You only need fibers in the direction of the load for that specific load case. So you don't. So this is how you can then optimize your layup for your structure. So we move on to open hole analysis. So open hole analysis is all to do with stress concentrations and composites. So normally for static analysis, we ignore stress concentrations due to holes because of if we use isotropic materials, because of the plasticity that you get with isotropic materials. But for composites, stress concentrations are a real thing because they are all, mainly composite materials are all linear, got all linear behavior. So stress concentration is a real thing in if you want to do static analysis. Just back to isotropics, we don't ignore stress concentrations because we use that for fatigue analysis, but not necessarily for static analysis. All right, coming back to the composites. So typically your stress concentration is a function of your layup and the direction of your load applied relative to the layup directions. So in this case, if the load is applied at an angle, 90 angle, then you get a stress concentration of 2.4, and your load distribution around the hole typically looks something like that. If it's applied at an angle 90 degree, the stress concentration is 2.44, and typically your load distribution looks like that around the hole. And as it applied at a 45 degrees, the stress concentration is 3.49, and that is typically what the load distribution looks like. So this tells you you need to know what is your load directions, what's your hole size, all of that, and your stress state to be able to analyze the stress concentration and failure around a hole in composites. So the method that we employ in DFC is documented in Stress Concentrations in Laminate Composites by Tan. So it's a very nice book, comprehensive book addressing stress concentrations and failure criteria, etc. So it's a very nice book. So if you can get a hold of it, do it. So there's a method in that book that gives you basically a set of equations on how to calculate the stresses around a hole given a load direction. So that's just a breakdown of the basic equations that's done, and all of this whole methods is being validated by testing, etc., etc. Right. So the basic theory is that the composite does not fail at the hole; it fails at a distance away from the hole. So there are basically two criterion. One is the average stress criterion. That gives you a characteristic dimension A0 from where you need to extract stresses to be able to calculate the RF. And then there's the point stress criterion, which also gives you a characteristic dimension D0, gives you the location of where you need to extract stresses to do the RF calculation. So the process is then basically you calculate the laminate price stresses at those two dimensions. Those two dimensions are actually determined by test, and it's driven by your hole size and the layup that you want to use for your structure. So you need to do some testing to define those two dimensions. You can either use one or both criteria or just one of them, doesn't matter. And then you employ the basic formulas, and you calculate the stress state around the hole at various angles around the hole, basically from 0 to 360 degrees. And each angle you get a set of stresses, your sigma 1, sigma 2, sigma 1, 2 at a specific angle. And then you use those stresses with the standard failure criteria like Hill, and you can calculate an RF. So this is typically your stress state around the hole, and this is then typically your RF state around the hole at each angle. So you can see in this case here, somewhere roughly 40 degrees, this is where you get failure. 40 or 180, 140, blah, blah, blah. So this is where you get your min RF around the hole. So the way we then implement this into DFC and Apex, typically you'll get your geometry will have a hole in it, and then you will defeature that hole and you create a seed point. So we use that seed point to define the location of the open hole analysis. We're assigning an open hole analysis ID to that point. You simply rename the point. And this is the data that you need. You need to give it a width and a diameter, and whether you want to use the point stress or average stress criterion, and you specify how many points around the hole you want to analyze. In this case, we do it for every degree. And then once we extract the open hole data, then we find the elements connected to that point. So it will normally be 4 or 3 elements. And we use the loads of those elements then to do the open hole analysis, because that gives us the load without the hole. And then we use that then to calculate the stresses with the hole using the method. Right, so in developing this thing, so because Nastran is perfectly modeling stress concentrations, we can use Nastran actually to do that. But for that, you need to model your hole very fine to extract the stresses around the hole, and then you can use your standard methods like the RF criteria like Hill to calculate the RFs. So in this case, the elements that we've extracted there is located at a naught distance of 3.5. So we specifically created the model for that. And we get an RF of 0.67. And typically you can see it ties up very nicely with our predicted RF distribution. So so it will go from high to negative or to failure around about minimum RF around about 40 degrees. So that's typically what you see here. And then for these areas, then up to 180, you get the problems area, and then you just repeat that. So there's good correlation between a FEM result and what we get with the theory. And then we've done then is extracted data here and data here to do the theoretical calculation. So in theory, putting that into the actual coded method, we get, or typed up method, you get an RF of 0.66. And when you use the DFC method, we get an RF of 0.64. So you can see they all of them pretty much ties up very nicely with each other. Right, so again, all methods and the calculation process are documented with references, and they are available to DFC users for evaluation. DFC methods, again, we can customize it, and calculations can be tailored to user requirements. So we can tailor your methods if you have got different ways of doing it, etc. Then we can incorporate that into DFC. Okay, thank you. So that's just a quick overview of DFC's composite analysis capabilities. Zak, should I move on?
Thank you, JJ. Maybe we can, what's your preference? Do you want to do maybe a quick Q&A, or should we do all of it at the end?
I think let's leave it till the end just so that we have enough time.
Sure. Okay. Then we can continue with your second part.
Right, so let's have a look at the dynamic analysis capabilities of DFC. So what is a dynamic analysis? So it's basically a Nastran 𝗀𝗧𝗧𝗏 solution, which calculates the dynamic response of a system subject to forcing frequencies. So there are basically two ways of doing it. Let's do a frequency response analysis. So that is more or less equivalent to a sinusoidal input. We have various frequency. We have a set frequency and a magnitude. And then you have a random response analysis. So there's no set frequency. There's no set magnitudes. It's everything is random. So that is a random response analysis. And typically what you'll get from the output is a response graph, which tells you how your system is responding to your forcing frequencies, and these peaks you will typically get at the natural frequencies of your system. So there will be some amplification, and you'll get a big response there. So you are interested in looking at these peaks. So the value added by DFC is that we have a very convenient way of creating the input data required for 𝗀𝗏𝗏, and we add the data automatically to the BDF. We combine dynamic loads. So normally these loads you specify by axis, X, Y, or Z axis, and then you later on need to combine them to get a resultant load. So this is what we do. We can also take that data and we combine them with a static load if there's a static load occurring at the same time as the dynamic loads. And once now that we have loads, we can now analyze your structure with all methods available in DFC for that combined loading. So again, DFC manages the process in a simplified, standardized, and automated way, reduce cost and save you time. Right, so we're going to look at our convenient way of creating the 𝗀𝗏𝗏𝗏 input data, automatic creation of the BDFs, how do we do load combinations, and then we also have a feature that you can actually look at the response graphs of the combined loads. Right, looking at, again, our RF calculation, our allowables are, you obtain that from test data, but this method is mainly focused on how to get the applied loads. How we combine loads and then extract that loads for analysis using the methods. Right, so in terms of input data for PSDs, for random response analysis, so we have just a tabular input that you can add all your PSD data for each excitation axis. So we have that, you just type those data into DFC directly to get your PSD graph. Then in terms of the combined data for random and frequency response analysis, so basically you define your start frequencies and end frequencies, add your integral vector. Then we have 3 frequency options, frequency cards, namely a FREQ1 and FREQ4, which you define the data in here. You select your PSD, select your magnitude for frequency response, select this excitation axis, and you add your damping type and damping value to this table. So this is the extent that you need to do to define the analysis. We then, once you create the scenario via DFC, we then automatically add those cards to the BDF based on the input data. We add all the case control data as required, and we use a handy parameter, thank you, Gerrit, called mode select. So normally with these analysis, you end up with thousands of frequencies that you need to analyze with response data. And what the mode select card does, it filters those frequencies just to find the frequencies that contributes to 90% of the modal effective mass. And then from thousands of frequencies, you end up with probably about roughly 80 frequencies. So what that does, it drastically reduces your runtime and the size of the results files, because these files can typically run into terabytes. And now you can minimize this to gigabytes. Right, so in terms of load combinations, so what we do here is we use the European Corporation for Space Standardization. So they've got a method on how to take all those loads and how to combine them. So that's the method that we employ. So again, how we do it is there's a table inside DFC, which then you specify the combination factors. So we can combine random and frequency response and static loads into one result. This is how we combine it. We combine the random and frequency response into one result. So for random analysis, the typical data that you get from a random analysis is RMS data. And you need to multiply that with some form of a factor. And typically that factor is 3, which is typically the 3 sigma factor. And that will give you an equivalent static load for the random data you can use for analysis. And then what we do is these data are normally an X, Y, and Z axis. So we then combine the X, Y, Z data in a quadratic way using the 3 sigma values. And then we get a resultant load or stress. Frequency results. So there are 3 options that are given. So the most conservative option is that you just use magnitudes. You ignore phase and frequency in these results. So these results are a combination or are complex numbers. So it's a combination of real and imaginary data. So the most conservative way is you ignore the phase and frequency, and you just use the magnitudes. The middle option is you use a linear combination of magnitudes by frequency, ignoring phase, and then the most time-consuming process is you do not ignore frequency, phase, and frequency. So you do some fancy calculation to get your magnitudes from them. So those are the three options. So we take the middle option. We ignore phase and we just calculate the magnitude, and we add the data by frequency to get the resultant loading at the three axes. Then we combine the random response and frequency response data, either linear or quadratic. So those are more or less the methods given in the reference documents. So again, what we do is we create a H5 file with a combined dynamic results, which is a combination of your random and frequency response data for each analysis axis. And then that H5 file, we create an H5 file, and you can import that into Patran or Apex, and you can do some post-processing there. So this is just basically a summary of what I've just explained. Random results is a quadratic combination of each of the axis values, and then frequency response data, you can either add linear, quadratic, and then you can get your combined random and frequency response data, either linear, quadratic combination of that. Right, so then when combine it with static results, so all your dynamic data is now all absolute values. In this case, this is just a 2D stress output for a 2D element. So now you have your static loads. You've got your sigma x, sigma y, and your shear stress, and you want to combine that with dynamic data. So now for the dynamic data, now you need to consider all possible sign combinations of that dynamic data to be combined with your static data. So this is then just an example of how we do that. So you have got the XY and XY stresses. Here we have all the possible sign combinations of it that we've combined to our static load to get to a resultant load. And from that, then afterwards, you can calculate your � stresses or principal stresses, etc., as you normally will do. But that's done after all the combinations is done. You can't combine volumetric stresses with each other. You have to do that afterwards. Right, so now we have load data, and now we can use those loads to calculate RFs using any of the DFC methods, composites, metallics, joints, fasteners, glue joints, beams, etc. Just one limitation, that is the 3D laminated 3D cores modeled in 3D. Unfortunately, that's something that we cannot analyze because you don't have a stress output for it for any composites, and you don't have force output for solid elements. So there's just one limitation there. Right, in terms of response graphs, so typically what we can produce is the max response per axis. So that will pick up the node ID at where we have a max response for each of the axes. And we calculate the RMS values, etc. So that you can, typically for random response analysis, so you can see your peaks. But this will just give you the maximum response for a specific node. What we actually a more interesting graph is actually to look at the envelope. So we create then an envelope per frequency. What is the max response at the specific frequency? And then you get something like this. So this is a little bit more, gives you a little bit more information than just a maximum response. So this gives you the envelope. So this is a very handy graph to have to evaluate the response of your structure. Right, thank you. So that's it. So that's composites and dynamic analysis.
Great stuff. Thank you, JJ. See, we have a few minutes left for questions. 𝗏𝗏 Ghrinling, I assume your question is going to be on composites by reading your mind via Teams.
Yes, good morning. The frequency response, does that mean we can use a similar model to predict Flutter behavior?
No, for Flutter is a different subject. So for there, you need to probably use something like flight loads. It's got a specific module, Nastran solution to predict Flutter behavior. So I would not use the results to try to predict Flutter. I would rather use the flight loads because it's much more involved than just a dynamic response.
𝗏𝗏, are you happy?
For now, yes, thank you.
Sure. Yes, our friends at BIAS is with us again. Esref, you're more than welcome to state your question. Esref, you're muted.
How's it, JJ?
Okay, Marco,
sorry.
go for it.
How's it, Marco?
Yeah, just my experience with composite fasteners and holes and stuff. In all my years, we've actually done testing. So we make a design principle that we will use in the design, lay it up and test it to get your A and B bases allowables for the composites and that type of stuff. I don't know how accurate your analysis here does that map. Have you had any experience like that?
All right, so this is purely open hole data. So
not filled hole. Okay.
No, not filled hole. So I'm just addressing an open hole situation here. For filled hole, yes, I agree with you. That is normally you need to do testing with that.
Okay. No. Okay. No problem.
And that stuff is normally not available public domain.
Yeah.
Because it's expensive, so people keep them for themselves. So I'm not addressing filled hole at all.
Okay. No problem.
Any other questions or comments from you, Marco?
No, I just need your help somewhere along in the future on other things. Okay.
No, 100%. I need to visit you guys very soon as well.
Okay.
Esra, if you had a question, please.
Yeah, I kind of muted myself, I think. Can you hear me now?
Yeah, we can hear you.
Not sure why that happened. So you have everything established in this tool, but it doesn't include the core, the composite core modeled as 3D with solid elements. What was the challenge with that? Why couldn't you include that one, for example? Like, is there a specific reason? Just curious.
Yeah, so the first one is and that's purely dynamic analysis. Okay. So SOL 111. So SOL 111 does not support any form of composite stress output. So if you model a core with a 𝗶𝗀𝗶𝗴𝗄, which is a 3D layered solid, then you don't have any stress output. Then a solid element does not have force output. So you can't get stresses, you can't get forces, so you can't calculate the core in a SOL 111 when using a 𝗶𝗀𝗶𝗴𝗄 element. So the way to go around it, which I have not yet investigated, but it's to use a 𝗶 or P solid, and you assign a mat9 material to it. Then you could probably do something there. Because then it's not a layered, layered solid, layered composite. Then it's you need to make some adjustment to your P solid properties using the mat9 to be able then to extract the stresses, and then you can do a 3D core analysis. But that I have not yet explored. But the way I've done it in the past, it's not possible.
Yeah, that wouldn't be very accurate though. Thank you.
All right, see your hand is up. Go for it.
Yes, I just want to make sure DFC is not included with the MSC one suit. This is an additional cost package, right?
On this day and date and time, it's additional to MSC1. However, it is developed in partnership with the whole MSC1 team. So it's very much integrated into MSC Apex, Nastran, and Patran.
Yes, I remember that. But okay, that's good. Thank you.
We can take the discussion and the negotiations around that offline, Gerrit.
Yeah, of course. I don't think I have an immediate need for this. I just wanted to double check.
Sure, 100%. Cool. If there's no other questions, you can close off. So if any of you hasn't seen the prequels of this session, we have them on our YouTube channel as discussed in the beginning of this session. You're more than welcome to have a look at that. This session will also be included there within the next few days. Otherwise, please connect with us on LinkedIn to see any updates on product developments, features, and updates. And yeah, you're more than welcome to contact us directly as well regarding questions on DFC software or anything else on MSC1. Thanks, everyone. Thanks, JJ, for your time, your inputs, and your insights into the engineering behind the principles, as well as the how it is integrated and coded into DFC as well. Cool. We'll be in touch.
Thanks.
Sorry, JJ, go ahead.
Yeah, just from my side then, Zak, thank you for you guys for facilitating these webinars, and then thank you for everybody who took the time to have a look at my boring stuff.
It's
Thank you very
definitely
much.
not boring.
Okay. See you guys.
Cool.